In this video we're going to look at network topologies and protocols. Before watching this video you should be familiar with all the stuff in Unit 1.4 covering all the network devices and some more of the network basics. So the big question is, what is a topology? A topology is basically how all the different devices on a network are connected together. There's several different ways of connecting the devices. There's several more than you need to know for the GCSE course, which we aren't going to cover. But a lot of the ways that you will find are pretty much antiquated by now. They're not really used. And if you do see them used, it'll be in some sort of legacy system. Now, a term that you'll hear quite a lot during these slides is the term node, and a node is simply any device that might be connected to a network. It could be a desktop computer, laptop, printer, switch, a server, it could be a smart TV, a games console. With topologies, it doesn't really matter what the node is, it connects to the network. There's only some topologies where the specific node really does matter, and we'll have a look at that when we get to it. Now, in terms of the exam, the things that you really need to know about all of these upcoming topologies are the basic layout of how they're set out, which two topologies we wouldn't really use anymore, or you physically can't make anymore because we don't make the components that allow us to make them, and the strengths and weaknesses, why you might use one over another. So bear that in mind as we go through these different slides. On each one I do have a pros and cons table which overviews some of the benefits and drawbacks of each one. The first topology we're going to look at is the bus topology. Now, if you look at the image in the top right hand corner, you can see that we've got several nodes, which are the circles connected to what we call a backbone cable. So each one is connected in series, and the data between these different nodes can travel in both directions. So one computer at the end can send data across the backbone, and data can also be travelling in the opposite direction. At either end of the bus network there needs to be a special device called a terminator, and what this does is it stops the data hitting the end of the line and then reflecting back down the cable, causing trouble across the network. Now, these are very rarely used anymore, and if any of them are in operation now, it might be a bank where they have to use some sort of old terminal computers to manage some very old system that has yet to be updated. Now, a quick overview of your pros and cons. Back in the time that these were used, the cost of cabling and setting up computers was quite a concern. So your main pro is that because each of them are connected to one backbone cable running the stretch of the network, there's very minimal cabling to connect all these computers. However, you do have the cons of if you need to add a computer to that network, say for instance you needed to insert a computer between the two on the left hand side of the bus network, you'd have to take the network offline in order to add it to that backbone cable. Because data can travel in both directions, you can get situations where the data collides with each other and essentially corrupts itself. So data might have to be sent across the network multiple times before it's received in a working order. And finally, using the backbone line means that the nodes can have to transmit data much slower than if they had a dedicated line to each one, because they've got to wait to be able to use that backbone line, and if the two try and use it at the same time, you can get data collisions. The ring topology is very similar to the bus network in the way that the computers connect to each other. Instead of having a backbone that has two terminal ends, it loops around, forming a ring. Now, as opposed to the bus network, the data only travels in one position, and the data has to pass through each individual computer on its way. Now, this can cause some issues in terms of security, and can also take up extra processing time on each of these computers as the data passes through them, because the computer needs to make the decision on whether or not that data is for itself or if it needs to pass it on to the next computer in the line. Now, because it only travels in one direction, and to avoid there being so much traffic that becomes overwhelmed, only one computer can send data at a time, and it's often managed by something called a token. And the token passes between each computer, and that token gives that computer the ability to send data out to another computer on the network. If a computer is waiting for that token, it essentially cannot send data on that network. Now, the ring network is very, very, very rarely used, same as the bus network. So again, if you would ever see this one working in real life, it would be in some sort of legacy system where the company or the organisation requires incredibly old computers or software that's only been written for very old computers enabled to run that particular system. Now, similarly as the bus network, the pros for this is that you've got very little cabling. As you see in the little diagram in the top right hand corner, you need a cable that runs from one computer to the next. In terms of cons, again, the network needs to be taken offline in order to add a computer. You've got to break the ring network in order to add an extra computer to it. So if it takes you half a day to add a computer to that ring network, that's half a day lost in terms of network connectivity. Now, while the ring network has solved the issue of data collisions going across a backbone on a bus network, the solution is only one computer can transmit data at any one time. Now, if you've got other computers on the network that require the use of the network, they're going to have to wait their turn. And because data has to pass through each computer, it takes up processing time on each of those computers, having to sort of make the decision whether or not that data is for it or it needs to be passed on to the next computer. And a major issue with the ring topology is if one of those nodes, one of those little pink circles, fails, the network can no longer work, because the data can only travel in one particular direction, and it would hit a broken node and the data would essentially finish there. So if one of those nodes fails, the star topology is one of the topologies that is used today. Now, there's only one more that we're going to learn about after this, but these two that we're going to cover now are particularly important. So looking at the diagram below with the pink circles and the white lines, each node has a dedicated connection to a central computing device, a central node. Now, most of the time this node will be a switch. Sometimes it might be some form of server, but 99% of the time it's going to be a switch. And because each one has a dedicated line to that switch, they can send and receive data pretty much simultaneously. Now, a node that no longer works on that network, providing it's not that central switch, means that there's very minimal impact on that network. Obviously, if the node that fails is a printer, you're not going to be able to print anymore, but in terms of the rest of the network being able to function without it, it should be able to continue with minimal disruption. Now, this sort of topology is the sort that you'll find in most organisations, at school, and pretty much anywhere where you have a fixed computer network. So if you think about at school, each of those computers has a direct cable that leads eventually to some form of other node, more often than not a switch. So it's an incredibly popular type of topology, and it's essentially replaced the ring and the bus network of that we used in the past. Now, there's a lot of pros to the star network, so it's much more resilient, as we've already said, to network failure. So thinking about those dedicated lines, if one of those lines fails or one of those computers fails, the rest of the network should be able to continue on. Now, because each one has got one of those dedicated cables, the data can move much faster. You're not having to have computers share a particular route or a particular cable, so there's much less network congestion. And an issue that was with the previous topologies. Adding a node is as simple as plugging in another cable into the switch, and it doesn't mean you have to take the rest of the network offline. In terms of cons, you've got a lot more cabling. So if you think about your classroom at school, if you've got 30 computers in a room, each one of those might have to have a 30-40 metre cable in order for it to reach a switch. Now if there was a ring topology, you just need a cable to run around each one of those computers, and it'd be much cheaper and much less expensive in order to set that network up. Now, the added complexity of running a star network also requires you to have some sort of network switch where all of them can be plugged into. Now, network switches, even though they've come down in price significantly over the past 10 years, is still a fairly expensive piece of kit in order to get your network running. The final topology that you need to know for your exam is the mesh topology. Now, if you look at the image in the bottom right hand corner, you can see that each node is connected to a number of other nodes, and the whole idea is that you don't need a switch in order to connect each of the nodes together, and they can pass data on between each other if needed. Now, the image there shows just a full mesh network. If you had a partial network where each one wasn't connected to every other node, the nodes could pass data between each other until they get to their desired location. Now, the number of the connections on there makes it incredibly reliable. So if one connection was to fail, or one of the nodes was to fail, the data could be passed on through the other ones, and it would try and find the most optimum route to get to its destination. Now, it's a relatively new topology, and if you just simply look at the image, you could guess how much it would cost to cable a network like this. Most of these types of networks are actually wireless. An area where mesh topologies are quite common is in home automation. So if you get yourself some of those fancy wireless light bulbs, more often than not they connect using a radio type called Zigbee, and Zigbee forms a mesh network between the different light bulbs so they can pass on the information. So the little box that you might get with them might only reach the first couple of light bulbs in your house, but those light bulbs can pass on the command to the other ones. Now, your pros of a mesh network is that it's incredibly reliable due to the large number of connections between each node. And if one fails, or one cannot quite reach, a signal can't quite reach the intended destination, the other nodes can help pass that message on by repeating it. It does, however, if you wanted a wired one, require a lot of cabling. So again, you would probably only see this sort of network in a wireless sort of scenario. And because of the complexity of them, if you weren't buying an off-the-shelf package and you wanted to set your own up, you would probably need some sort of specialist, or you need to take a lot of time researching how you would go about best setting one of these up. Now, before we look at some different protocols, what we'll do is we'll have a quick look at how we'd connect different nodes to one of these topologies wirelessly. So, as you probably will have figured out, Wi-Fi is the standard for connecting devices to networks wirelessly. All your phones, all your different games consoles, televisions, computers, laptops, pretty much all of them now will have some way of connecting to a Wi-Fi network. Now, Wi-Fi uses radio waves to transmit data pretty much in the same way that an audio radio in a car would work, how TVs get regular TV channels, and so on. Radio waves are broken down into different frequencies, which are often given numbers, and frequencies are often banded together in groups for particular purposes. So Wi-Fi uses the 2.4 GHz band and the 5 GHz band. And within each of these frequency bands, it's broken down further into what we call channels. And the easiest way to think about this is that you've got channels on your TV, and by changing the channel, you're adjusting very slightly the different frequency that the TV's picking up the signal from. Now, from the very, very earliest versions of Wi-Fi it has used the 2.4 gigahertz band. Now, the reasons for this are very historical. Most radio frequencies are quite heavily regulated, which means that you need a license or permission from a government agency in order to broadcast a signal on them. Now, the 2.4 gigahertz frequency band is unlicensed, which means that you don't need permission in order to create devices that broadcast on that particular band. And the reason it's unlicensed is because in the 50s, when they started to make microwave ovens, the frequency that microwave ovens work at is 2.4 gigahertz. And because the frequencies from those microwaves leak out, it would make it a very poor decision to use for very official purposes. Now, for Wi-Fi using the 2.4 gigahertz frequency band, it's very good at penetrating walls. So it can travel through multiple walls before the signal becomes too weak to actually form any useful data. A problem 2.4 gigahertz band does have is that there is a lot of overlapping channels. So when they set these channels up, they probably were expecting Wi-Fi to be as common as it is now. So if you look at the picture below, you can see the channels 1 through to 14, and all of them pretty much overlap another channel. Now, there are only 3 channels that don't overlap at all. You've got the 1, 6, and 11 channels. So a lot of Wi-Fi wireless access points will try and make use of those channels and figure out what the best channel is for that particular area. The 2.4 gigahertz frequency band also gets a lot of interference from other devices. So if you've got a microwave running, you're going to get slow performance. If you've got any other devices that use that same band, such as baby monitors and other sort of cheap wireless devices that you might have around the house, then you're going to get much worse Wi-Fi performance. And it might be why your Wi-Fi network is slower or doesn't quite reach particular areas of your house. Now, in recent years, Wi-Fi devices have been able to use the 5 gigahertz frequency band, mainly in answer to the issues that they get on the 2.4 gigahertz with the interference. Now, 5 gigahertz can run at higher speeds, but it cannot penetrate walls as easily, and you tend to find that it has a much shorter range. So it could be that if you get an interference on 2.4 gigahertz, switch over to 5, but there's too many walls in between you and your wireless access point. Now, none of the channels on that 5 gigahertz band actually overlap. So if you pick a channel, the chances are that you're not going to get any interference of other Wi-Fi networks in your local area. But as a drawback, only modern devices tend to have this. So even thinking back to the original PlayStation 4, the PlayStation 4 didn't have that 5 gigahertz band. They've added it in recent years, but if you had one of the earlier devices, even though it was only 7-8 years ago, it doesn't have the hardware to run it. If you get a device nowadays, you tend to find that it has this band, so you can access, hopefully, higher quality Wi-Fi signals. One final feature about Wi-Fi that you need to be aware of is encryption. Now, radio waves are private, and you can tend to find, just like with the radio in your car or TV channels on the TV, anyone can access them. And that's why Wi-Fi in the protocol has to have some form of security and encryption in order to protect the data. Now, this is often why when you connect to a network, you have to put a password in. It's essentially you using your key in order to access the encrypted data. There are several different encryption standards. You've got WEP, WPA, WPA2, and WPA3. There are some more less known forms of encryption that might just be used for enterprise-specific domains. WEP and WPA are the oldest forms of encryption on Wi-Fi, and we tend to find now that they're too weak to actually use, and that data sent across those sorts of networks are protected by those forms of encryption are not considered secure in the slightest, as they can be mathematically defeated. And that's to say, instead of trying to randomly guess the passwords, there are ways to circumvent the encryption that's applied to those networks. WPA2 is quite widely used. There has been issues with it over the past few years with the ways different manufacturers implement it on their devices. There are ways, if the devices have not been updated in the past year, where a hacker may be able to get onto that network and start viewing the data on it. But the most recently released form of encryption is WPA3. And as of now, there has been no really known cases of people circumventing that form of encryption to be able to get access to a Wi-Fi network. If you don't have that password to put in and you don't have that encryption on the network, the data is essentially unencrypted and anyone is able to read that data. So if you're in a coffee shop and you don't have to put a password in, you should consider the data that you're sending on that network to essentially be able to be read by anyone else who's on that network. And you shouldn't trust it for secure applications such as online banking or logging into secure accounts. Now, moving on to the protocol part of this unit, before we look at any specific protocols, we need to understand how computers actually send data to other computers and how they identify other computers that the data might need to be sent to. So there are two different methods for sending and identifying computers on a network, and you've got IP addresses, which you might be familiar with if you've been on the internet and you've maybe set up your own networks at home or connected your devices to a network. And you also have MAC addresses, which are a little bit more hidden in the network setup, and you don't often have to come across. So every device that connects to a network, either by Ethernet, by Wi-Fi, even Bluetooth, has a unique hard-coded address called a MAC address. Each MAC address is pretty much unique. Even worldwide, the device manufacturers have a set number of MAC addresses they can use, and they need to make sure that each one is unique. Now, that address can either be 48 or 64 bits wide, and is often, as you can see at the top, is represented in hexadecimal to make it a bit more human friendly so it doesn't take up the whole screen being able to read it. Now, MAC addresses, quite simply, are used for directing traffic to computers on the same network. So if you've got a network at home, your little multifunction device, your little what would be referred to as a router, would use the MAC addresses to identify the different computers and transmit data between them. Now, the way that it does this is that little box will know that all of the MAC addresses of the devices connected to it, and essentially has a table which they line up the MAC addresses to the port that those devices are plugged into, so they know if packets are destined to go to one MAC address, they know which port to send that data down. So if we have a look at the table, you can see you've got different MAC addresses, and on the right hand side you've got the port that they are connected to. Obviously it's a little bit different if you're using Wi-Fi, but they will still have this table that they will use to direct different packets to different computers. IP addresses, on the other hand, are used for communication between different networks. So they're mainly used to direct internet traffic. Now, most IP addresses are 32 bits, but over the years to come, we're going to see a lot more 128-bit wide IP addresses, which are referred to as IPv4 for 32-bit and IPv6 for 128 bits. Now, IP addresses are hierarchical, which means that it tends to be that it makes it a little bit easier to locate a specific device, while MAC addresses are sequential and they go up one by one. IP addresses are broken up into 4 separate sections. So if we look at this IP address here, that's an IPv4 IP address. If you want to send some data to that computer that's got that IP address, the first thing you would do is you would send that data to an internet router that has the IP address which is 5.1, and you'd ignore the rest of it. And once it's on a 5.1 router, that router can then direct it to a 114 router, which has got that same 114 address, and so on until we get down to 200 and then 99. Now, a lot of countries have specific IP address ranges, so one particular country might have the 5.1 IP addresses, so you know roundabouts where that router is and where you need to send that data in order to find that computer. Within the IPv4 range of IP addresses, you can have dynamic and static IP addresses. So a dynamic IP address is one that changes every single time a device connects to a network, and you've got static ones where the device is remembered and it gets the specific static IP address each time. Now, the reason why we might have dynamic IP addresses is that in IPv4 there are only a limited number of IP addresses that we can assign, and if I remember rightly, it's about 4 billion. Now, there are more than 4 billion devices in the world that can use an IPv4 address. So if one device is not using a particular IP address, it can be reassigned to one that is, in order to allow us to still continue functioning on networks. IPv6, on the other hand, where there's 128 bits to assign to a particular device, there are more than enough IP addresses to even assign one to each piece of sand on the entire Earth, and there'd still be plenty left over. So theoretically, we're not going to run out of IPv6 addresses anytime soon. Now we know how to address data to the correct places, we need to know how, when the data gets there, we know that it can actually be understood by the computer. Now, what we have to do this is something called protocols. Protocols are just a set of rules for how computers should communicate. It should stipulate how communication starts, how it ends, how the data is organised when it is sent, and if the data is not received in a way it expects, how a computer can request that the data is resent. Now, without protocols, many of the activities we do online would essentially not be able to work. For instance, requesting a web page takes a little bit more thinking than just clicking a button and expecting it to arrive. Things like streaming video and receiving email require even more thought in order to send that data to a computer. However, providing that the rules that we've set up are followed, communication between computers generally works pretty well. Now, the first protocol we'll look at is HTTP and HTTPS. These are quite common protocols that are quite visible to the end user because of the way they appear in the URL in a browser bar if you look at the image at the bottom. Now, HTTP is Hypertext Transfer Protocol. It's the protocol we use to request and send web pages over the internet. It can also be used to request particular bits of information if an app requires information off a web server. The secure form of it, HTTPS, adds encryption to this protocol, which means the data that's transferred can be done so securely without it being stolen. Without HTTPS, you shouldn't be able to send anything like credit card details over the internet because it could be intercepted and be used by an attacker. Now, in addition to just requesting and transferring web pages, the HTTPS also has rules about how it negotiates what we call a handshake, which is essentially the computers agreeing on a way of encrypting the data and being able to decrypt it when it arrives there. And that's not an easy process. Nowadays, websites use the HTTP2 protocol, which is an improved version of HTTP, which has encryption by default, but also allows for things such as parallel file transfers, whereby the old HTTP protocol, each transfer of each file that was required for the web page essentially went one after the other, and that's why you saw pages in olden times sort of draw themselves on the screen, because images would load one after the other. With HTTP2, they can arrive in parallel, which makes browsing the internet a little bit quicker. Another relatively common protocol is FTP, or File Transfer Protocol. It's the protocol that manages how files are transferred between computers and web servers on the internet. So if you design a website on your computer, you need a method of uploading it to a web server where then it can be put on the internet. It also has features built into it for modifying files locally on the server, moving them around, and also deleting them. Just like HTTP, there is a secure version, File Transfer Protocol Secure, which works in a similar manner to HTTPS. Where protocols get a little bit more confusing is with the mail protocols. There are numerous different ways of managing email on the internet. There's one protocol for sending emails, however there's two for receiving, and I'll show you what I mean. SMTP is a protocol used for sending email between servers, and that's pretty much standard. That has not really changed in the many years of being able to send emails. So if you send an email, it goes to the server uses SMTP to send it onto the server that needs to receive it for the recipient. Now, with receiving email as in off the server for the user could either use POP, which downloads all the messages off the server and then deletes them off the server, or you can use IMAP. And the way that IMAP works is it syncs the mail with the server, so each device has a copy of whatever's on the server. Now, the reason why there's two of them is back when email started being a thing, storage was a lot more expensive, so you would try and delete the emails as soon as you were done with them, and you wouldn't want them hanging around on the server taking up storage. Nowadays, that storage isn't really an issue. People have a lot of devices, and they want to keep all of them in sync, so you don't just have one email on one device and the rest of them on your other devices. So, because of people's different changing needs, we've mainly moved over to IMAP as opposed to POP. You can still use POP, but you will run into issues if you've got multiple devices that you want your emails on. A very common protocol, one that is probably not considered as well known as the mail protocols, FTP or HTTP, is Ethernet. Now, Ethernet is a low-level protocol, often confused with the type of cable that it's most commonly used on, which is twisted pair. So all the computers at school are connected using a twisted pair, but the way the data is transmitted across that cable is using Ethernet. Now, because it's a low-level protocol, it manages how data is formatted and transmitted across the cables. Now, most of the time, this is how it regulates the voltage and how it forms those ones and zeros that get transmitted across the cable. Now, because Ethernet is a protocol and not the cable, it means it can be used on different types of cables. So originally, it had been used on coaxial cables, which is very similar to how similar to the cables that you plug into the back of your TV to get terrestrial channels, but you can also use it on fibre optic cables as well, ones where you won't have a voltage but it'll regulate how the pulses of light are transmitted across the cable. All the protocols that we've talked about and many more fit into something that we call the TCP/IP model. Now, the idea is that within the model we've got different layers, and these different protocols can be slotted into a particular layer. Now, most of the ones we've talked about, like HTTP, FTP, the mail protocols, fit into the application layer. And the way that we've set it up means that protocols can be swapped out as and when needed without affecting the protocols below them. So if we have a quick look at the different layers and how we would go about actually building up a packet to send on a network. So in the TCP/IP model, we start off with the data that an application wants to send. So it could be a web browser wanting to use a HTTP protocol to request a web page. So the data is taken from that browser and it is passed on to the next level, which is the transport layer. Now, the transport layer is responsible for error checking, making sure that the data arrives in the right or in a particular order and that it can be reordered into the correct order so the data actually makes some sense. So it's given a TCP header and that's attached onto the data from the web browser. After that, we add an IP header on, which is all about the information about where it needs to go, how it can get back, and so on. And that is passed down to the link level, which is where our Ethernet protocol is. And what it does is it turns it into what we call an Ethernet frame. It's got a header on there and a footer, and essentially what we're using is MAC addresses in order to transmit it from one device to the next. So it might be from your computer to the multifunction device that connects you to the internet. And then that device will have a new header and footer which then sends it on to the next MAC address on that local network. Eventually, when it gets to its destination, it makes its way back up through the different layers and gets to the application it needs to. The whole point of having it layered up is that you can swap out any of the protocols for an equivalent one, and it doesn't matter to the protocol below. So in the way we said that HTTP2 is the protocol that a lot of websites use now to transmit websites between browser and the server, we could just swap out HTTP and HTTP2 and it doesn't make a difference to the transport layer, to the internet layer, or to the link layer. You can swap them out as and when needed. And similarly, you'll see on the transport layer, you've got TCP, but you've also got UDP as well. You can swap that out, and it doesn't make a difference to the IP layer or the link layer. Once our data has gone through the TCP IP model, it's picked up its transport header, it's picked up its IP header, it's picked up the header and footer from the Ethernet frame. We pass it on to something called a packet switch network. And this is essentially how all our networks on the internet and connected to the internet actually transmit the data. So we already know that the data is split up into packets and that our transport layer adds a number to each one so that if they arrive in a different order, we can rearrange them back into the right order so the data actually makes sense. Now, when we send out all these packets, they get sent between different routers on the internet, and some of them might go slightly different routes. It could be that on one route there's too much traffic and it sends half the packets another way. And hopefully they all eventually meet at where they're meant to get to, and then they're reordered depending on what order that they arrive in. Now, if a packet goes missing, the computer can re-request that the data is sent again. So if there's a particular few packets missing, after waiting so long for the packets to arrive, they can be requested that they're sent again so that the data can be completed. So to give you an idea of how this works, the diagram here shows 3 different packets. The router at node A might send it on 3 different routes, and the data eventually gets to the host. But then the host has to rearrange it into the right order so the data makes sense. Before we had packet switch networks, we had something called circuit switching. So back when telephones used to use an analog system, everyone would have a dedicated line to the telecom, and then someone inside that telecom called an operator would pick up the line. So you'd ring a particular number, you'd ask the operator to connect you to that number, and they would physically connect your line with their line, and that's a circuit switch network. You had to have a dedicated line to communicate with another particular person. And obviously data wasn't split up and sent on different routes because you just had one dedicated line. Now, because we didn't have a dedicated sort of extensive interconnected network, they had to be switched manually. Now, over time, we managed to replace these operators with computers, and we gave people much longer telephone numbers to cope with this. But this sort of model would not work on the internet because every time you wanted to connect to Google, to Facebook, you would need a connected direct line to them that was not shared with anyone else. Using the packet switch network, the lines can be shared with data from different users. So if you think about your house, you've got a line from your house, maybe using a fibre cable, maybe using old copper wired cable from the telephone if you have ADSL, and that connects to a cabinet at the end of your street, and those connections are condensed down maybe into a few different cables down from maybe 200 from your street, and those are passed on to your ISP. Your ISP may condense all those cables down and puts the data on fewer cables. Maybe those cables are higher performance and can send more data, having much higher bandwidth. So the idea is that we don't have to have dedicated lines everywhere. We can use the different routes between routers to send the data without requiring a lot of expensive cabling. So as you can see in the image on the right, just to review, your circuit switch network, you had dedicated lines. If you wanted to talk to someone would have to physically connect your line to someone else's, so you could physically sort of talk to them over that network.